So chapter 8 is bonding part 1. Chapter 9 then will be bonding part 2. So there's several different theories about how things bond and why things bond, what they end up looking like. So we are going to be covering the easiest to the more complicated theories of bonding. So in chapter 8, we'll cover the more simple ones, namely Lewis theory, and then in chapter 9, we'll go into Vesper theory, hybridization theory, molecular orbital theory, and such. So this is the first idea of bonding. We barely touched on bonding before in chapter 2. We just talked about ionic versus covalent, and only in the context of we need to know because the naming is different for ionic versus covalent. And we had this very simple of idea of, well, how do I know if it's ionic? So how do you know, just looking at the formula, if it's going to be an ionic compound? The dead giveaway. The what? Yeah, but how do you know from the formula it's a salt? Well, starts with a what? Metal. Starts with a metal, a positive cation. What's the only exception that does not start with a metal but is still ionic? Ammonium. Good. NH4. So those were the rules we did in chapter 2, which was all about looking at the formula to identify whether or not it's ionic or covalent. Now we're going to look into, well, why would some things become ionic? Why would they become covalent? And then we're going to quantify how can we calculate if the bond is going to be ionic or covalent. And we're going to see that there's actually some exceptions to that generalization that if it has a metal, it must be ionic. If it doesn't have a metal or ammonium, it must be covalent. So first of all, we're going to start with Lewis theory. And to understand Lewis theory, you first have to understand Lewis dot structures. So Lewis dot structures are showing how many valence electrons are there. So what's the maximum number of valence electrons? 8. Good. 8. So those are N, S, 2, and P6. So this is the valence electron shell configuration for which family? The noble gases. Good. Group 8. The noble gases, because it has 2 plus 6, 8 valence electrons. So in chapter 6, we learned that as far as energy levels go, these are actually not at the same energy level. P is a higher one. For Lewis theory, we're going to suspend that thought for a minute and just say, okay, any s orbital, and then there's how many orbitals in a P subshell? 3. Good. So we're just going to look at this in terms of, in generalization, in our valence shell, we have 4 orbitals. 4 orbitals. Each one can hold how many electrons? 2. And in chapter 6, we would fill the S's first before going over to the P's, because P's are at higher energy and everything except for what element? What's the only element that P's are the same energy as the S's? Was the only element that had a different chart of energies that was on the study guide. I said, make sure you know this table. It ended up not being on the test, but it's probably going to be on the final now that you guys are giving me blank looks. What is the only element that its energy levels depend only upon the principal quantum number n and the Bohr model? Bohr model only applied for what element? Hydrogen. Thank you. Hydrogen. Woo! You're thinking too hard about that one. So hydrogen, the S's and P's, as long as they're at the same principal n, are the same energy level. We're going to kind of borrow that, but for all of the elements. So we're going to say all 4 of these are the same energy. So we're going to follow that rule of 1 electron per orbital before we double up. But we're not going to write it in terms of the orbitals. We're going to write it around the element's symbol. So for example, say I have boron. I would write the symbol for boron, which is a B. How many valence electrons does boron have? 3. Good. So in group 3, it has 3 valence electrons. I'm going to show 3 dots. And if I look at any element, it's got 1, 2, 3, 4 sides to it. So I'm going to consider each of those sides one of these orbitals, and I'm going to follow the rule you have to have at least 1 in each orbital before you pair up. So I'm just going to put a dot on one side, dot on the second side, dot on the third side, leave the fourth side blank because I've only got 3 valence electrons. So this would be the Lewis dot structure for boron. Now, it doesn't really matter which side you start on. I could have started on the bottom. Doesn't really matter. Just start on one side and at least have one electron per side before you double up. So if I did, for example, oxygen, how many dots would be around oxygen? 6. So I'm going to put one per side, 1, 2, 3, 4. Then I'm going to go back and double up. 5, and I'm going to make the second one on the other side, just kind of spread them out. Again, you could have drawn this as the two doubled sides on the sides. So the top and bottom, these are same idea. So those are the Lewis dot structures for elements. To make the Lewis dot structure of an ion, you're just going to add or remove whatever the appropriate number of electrons are and then show your charge. So for example, aluminum. How many dots would go around aluminum? 3. It's in the same family as boron, group 3. So I put 3 dots. What ion does aluminum commonly become? Aluminum what? What charge? 3 plus. Good. It's got 13 electrons. It wants to be isoelectronic with neon, which has 10, so it's going to lose 3. So if I drew the Lewis dot structure for aluminum 3 plus, what would I change about my dots? I'd lose 3. So how many would I have left? 0. So the ion would just look like aluminum, and now I would have 3 plus. No more dots. This would be my Lewis dot structure for aluminum. So the Lewis dot structure for main group metals, when they become ions, should not have any more electrons, because main group metals have no valence electrons once they become ions, at least their most common charge, because they're all trying to be isoelectronic with the noble gas before them. Nonmetals, on the other hand, such as our oxygen over here, what does oxygen want to do when it becomes an ion? Wants to gain. So what is the most common charge for an oxygen ion? Oxygen what? 2 minus. So let's draw the Lewis dot structure for oxygen 2 minus. So here's our original oxygen. What am I going to change about it to make it oxygen 2 minus? Add 2 more. So now 1 there and 1 there. So it becomes oxygen, and now I have a total of 8 around it. And just like with the aluminum, I need to show the charge. But here's the trick. If I just put a 2 minus off to the side here, we're not sure. Am I saying one of those dots is 2 minus, or am I saying the whole compound, or the whole atom is 2 minus? So how might I show that that 2 minus applies to the whole thing? Put it in parentheses, or we're going to use brackets. But yeah, put it in brackets here. So that would be the Lewis dot structure for, I should put an equals so it doesn't look like those are more electrons, for the oxide ion. Any questions about drawing Lewis dot structures for elements versus ions? It's just the number of electrons in the valence shell. So on to section 8.2, which you're following the textbook, is on page 328, is the start of focusing on ionic bonding. So we're going to focus on anionic bonding first and then talk about covalent bonding. So we talked about ionic bonding as being the attractive force between oppositely charged forces. So for example, if I had, we'll just use our classic example of an ionic compound, sodium chloride. Sodium chloride is really the ion sodium plus and the ion chloride minus. So let's do it as a Lewis dot structure, minus. These two things interacting. When we put them together as a compound back in chapter 2, we left off the charges because they cancel. But now we're going to talk about, well, what's actually happening between these two things. So these two things feel attractive forces for each other. Switch colors real quick. So right here, I'm feeling this attraction in this space in between. It's attracted because I have positive charge to negative charge. What do we call the force between charged particles? What is that? Chapter 5. What is the energy between charged particles called? What kind of energy? No, chapter 5 was a couple chapters ago. It was electrostatic energy, and it was proportional to Q1 Q2 divided by the distance between them. So Q1 and Q2 were the charges, D was the distance. As I pull them further apart, what happens to the energy? It gets what? Weaker. As I bring them closer together, it gets stronger. As I increase the charges on the particles, it gets what? If I have stronger charges, so instead of +1 and -1, say +2 and -2, would I have a stronger force or a weaker force? Stronger force, because I'm making stronger magnets. These charges are the force of the magnets. Stronger magnets attract stronger. If I make the charges smaller, it becomes weaker. So that was chapter 5. Now we're going to talk about this in terms of the force between them. This is called Coulomb's law, and I'm going to take this equation and I'm just going to vary just a little bit to make it for a force instead of an energy. It's still going to be proportional to Q1, Q2, but I'm going to square the distance, and that is called Coulomb's law. The force is proportional to Q1 times Q2 divided by the distance squared. So this is going to tell us how strong is our ionic bond. Strong. The actual energy that we calculate associated with the strength of an ionic bond is called the lattice energy. Lattice energy. 2 T's. So the lattice energy is defined as the amount of energy it takes to break apart 1 mole of your ionic compound from its solid to its individual ions in their gas state. So switch real quick to the PowerPoint and show you what this would look like. Here. So here's an example of the reaction that I would see for a lattice energy. For example, I would have potassium here and iodide both have to be ionized and have to break apart. So right here, starting with potassium iodide solid, I would have to end up with the 2 ions charged and in their gas forms. So a couple different things are happening here. Number 1, these 2 things break apart from each other. Number 2, they both change matter. They go from the solid to the gas. And number 3, they both become ions. The potassium becomes a positive ion, the iodide becomes a negative ion. The energies associated with these processes are all energies we have already seen. In the last chapter, chapter 7, what was the energy associated with making a positive ion called? Losing an electron to become a positive ion was called the what energy? Ionization energy, good. So that's the ionization energy. Whereas the iodide becomes a negative ion. What was the energy associated with gaining an electron to become a negative ion called? Electron affinity, good. So those are energies we've already talked about. And then we also have the energies of changing from a solid to a gas. I'll skip real quickly and show you. Here are the processes we would go through. Now, I am not, for this particular class at least, going to ask you to calculate the lattice energy. I'm more interested in can you compare it using Coulomb's law? But this is the process you would go about calculating it, just in case you see it on Learn Smart or something like that. This is called the Born-Haber cycle. So the Born-Haber cycle, you start again down here with your solid compound, and at the end of the cycle you have the 2 ions charged. And there are 5 processes they go through. The first process is going to be breaking apart into the individual compounds. In chapter 5, what did we call the energy it takes to make a compound from its elements? Hint right there. What does that delta HF mean? Standard enthalpy of formation. So that's we're going to take the negative of it because we're doing the opposite. Now, instead of forming sodium chloride, we're breaking it apart. So the opposite of the standard enthalpy of formation is the energy associated with the first step. Now, once we have the 2 separate compounds, we're going to need to take that sodium solid and make it a gas. So that's the standard enthalpy of formation of sodium gas. And we're going to need to take the chlorine and go from Cl2 to just Cl gas. So that's the standard enthalpy of formation for Cl. So these first three energies are all going to be from Appendix 2, those standard enthalpies of formation. For the compound, then for each of the individual elements as atoms, because standard enthalpy of formation for an element is only 0 if it's in its standard state. Standard state for sodium is a solid, not a gas, so I have to change it. Standard state for chlorine is a diatomic, not a monatomic Cl, so we have to change that as well. So that's the first three steps. The last two steps are making the two ions. So we just said the energy associated with making our positive ion is going to be our ionization energy, so that's IE1 right there for sodium. And then the standard enthalpy, the energy associated with making the negative ion is your electron affinity. So we made that negative because electron affinity is the amount of energy that is being what? Consumed or released. Released is the amount of energy being released. So if energy is being released, what do we do with this delta H value? Chapter 5. Delta H is what? Positive or negative for a energy being released? The system is releasing heat. Is that heat positive or negative? Negative, good. So that's why we put a negative in front of the electron affinity right there, because it's being released. So add up those 5 numbers, you will end up with the lattice energy for the compound. Again, I'm not going to ask you to do this just because there's a lot of steps. You might see it on Learn Smart, but I wanted you to at least be familiar with what the process was. I'm going to ask you more questions like which ones are going to have higher lattice energy, and you can determine that using our Coulomb's law here. Force is proportional to Q1, Q2. So let's look at that Coulomb's law there and break it apart and say, okay, what kind of generalizations can we make? So I think it will let me move it. Copy. Ah, yes. Paste. Haha, there we go. Which probably took more time than it would have taken just to write it again, but it's neat. So, Coulomb's law. The first part here is Q1 and Q2, the charges. So let's make a generalization. As the magnitude of the charges increases, the force of attraction does what? Increases or decreases? Attraction. I can spell attraction. Attraction. This is not. Thought I heard it earlier. Increases, good, because I'm making Q's bigger. So if Q and Q1 and Q2 get bigger, this whole number will get bigger, the force will get bigger. So the force of attraction increases. And the lattice energy what? Increases, good. So again, the lattice energy is how much energy it would take to break it apart. If there's stronger forces holding it together, just like stronger magnets, it'll take more energy to break it apart, so the lattice energy will be greater. So let's compare to lithium fluoride versus, let's say, magnesium oxide. Which has the greater lattice energy and why? Lithium fluoride versus magnesium oxide. Which compound has the greater lattice energy and why? Good, why? Good. I'm just going to put Le for lattice energy. Magnesium oxide would be the answer. What's the charge on a lithium? 1 plus. What's the charge on a fluoride? 1 minus. Good. What's the charge on a magnesium? 2 plus. And an oxide? 2 minus. So when I'm plugging into Coulomb's law here, Q1 and Q2 would be 1 and 1 for lithium fluoride and 2 and 2 for magnesium oxide. So we would expect, assuming that the sizes are relatively the same, which they are pretty close for these two compounds, that's why I picked them, we would expect that the lattice energy for magnesium oxide would be about how many times greater than for lithium fluoride? 2 or 4? Plug those Q's in. What do you get? If I plug in for lithium fluoride, they're both 1. 1 times 1 up here is 1. What if I plug in magnesium oxide? What do I get? 4. So I would expect approximately how many times greater? 4 times greater. And if we look up the literature values for the lattice energies, lithium fluoride has a lattice energy of approximately 1,017 kilojoules per mole, while magnesium oxide is not quite 4 times greater, but pretty close. Good. 3890 kilojoules per mole. So know the trend, because I will probably be asking you on the test ones that you do not have lattice energies for. You will have to actually use the trend to figure out which one's greater. Or I might ask you what's the reason behind it having greater lattice energy. And in this case, it'd be because the charges are greater. So that's the easy one. That's the first one. Check that first. Don't worry about the distance, because that's a smaller factor. Worry first about the charges. If the charges are different, that's always going to be what will determine which one has the greater lattice energy. Any questions about that one? All right, let's see what if instead of the charges being different, the distances are different. All right. So let's compare, and if you're following along, I'm on page 329 doing the example right in the middle of the page. Let's compare lithium iodide versus sodium iodide versus potassium iodide. The question is, which one would have the greatest lattice energy and which one would have the smallest lattice energy out of this grouping? You can't use the trick we used in the last case, because all of these have charges of +1 and -1. So the charges are the same for all 3 of these. So if the charges are the same, then what part of Coulomb's law am I interested in now? Distance. So how do we figure out the distance here? So we haven't really talked about bond length yet, but with an ionic compound, we're just going to simplify it down to the bond length is the distance from the nucleus of one atom to the nucleus of the other. So this radius plus that radius, so R1 plus R2 is equal to the bond length between the two of them. And I'm using that because do we know about the radius of ions? Or at least how to tell which one's bigger? Yeah, we did that in chapter 7. We just did that. We just took a test on that. So we know how to tell which one's going to have a bigger ionic radius. So the bigger the ionic radius, the what the distance between? Greater. Like radius. Bigger distance. Bigger distance equals what force? Smaller or bigger? If I make the distance between two magnets greater, what happens to the force I feel? Does it get weaker or stronger? Weaker. Or if I wanted to look at the math, distance is on the bottom of the denominator. That was redundant. It's on the denominator, which is on the bottom of the fraction. If I make the denominator bigger, what happens to my number? Gets smaller. Therefore, what happens to my force is I make my distance bigger. It gets weaker force. So if the force is weaker, what does that do to the lattice energy? Decrease, good. So lower lattice energy. Now you have two options here depending on how much you like the math and the numbers or how much you want to look at the concepts. You can go ahead and go back to the table we had in Chapter 7 and look up what the ionic radius is of each of these, ionic radii, plural. Or you can use the concept of trionic radius trends to figure out which one would be the biggest. Now, all three of these compounds have what in common? Iodide, which means that the second ion here, that would be our iodide, is the same for all of them, so they're all going to have the same radius. So I'm really just going to worry about the radius of the cation here. So sodium, lithium, and potassium, which one of these will have the smallest radius and why, without even looking up the numbers? Lithium, good, lithium. Why would lithium have the smallest radius? If you're looking on the periodic table, lithium, sodium, potassium, over there in group 1, we have, lithium, sodium, potassium, going down group 1 here, right? As you go down a family, what happens to your size? Gets bigger, because what happens each time you go down a row? Add a shell. So of these, lithium would have the smallest radius, and potassium would have the biggest radius. All right, so now let that dissolve for a minute and think. Therefore, which one would have the biggest lattice energy? Biggest lattice energy. We all feel like we've got an idea in our minds? So which one do we think is the biggest lattice energy? Lithium, good. Lithium, because it is the smallest radius, which means its distance is the smallest, so the magnets are the closest together, strongest force, biggest lattice energy. So lithium iodide would have the biggest lattice energy. Lattice energy, I'm just going to call it LE, lattice energy. Which would have the smallest lattice energy? Potassium iodide, smallest, because it has the smallest lattice energy, because it had the biggest ionic radius, therefore the magnets are the furthest apart. And if you look up the literature values for these, just to confirm, those lattice energies, lithium iodide had the lattice energy of 732. Sodium iodide right in the middle was 686. And potassium iodide, which we expect to be the smallest, was 632. Notice that compared to the last example, although we did get the trend right, how big was the difference in these lattice energies that differed only by distance compared to our last example that differed by the charge? Which one had a greater impact on the lattice energy? Changing the charges like our first example, or changing the distances like our second example? Charges. That's why I say always check the charge first, because if the charges are different, that has a greater impact on lattice energy than the distance. So check the charges first. If the charges are the same as it was in our second example, then look at the distances, because it does impact it, but not nearly as strongly as the charges do. How do we feel about lattice energies? Feel like, again, I'm not going to ask you on a homework or a test how to calculate these lattice energies. I'm just going to ask you which one would be greater and why, or maybe put an order of increasing or decreasing lattice energy. So you just need to be able to compare. Questions? Maybe feel like we're good with ionic bonding. Let's do another example. Go over the PowerPoint, do their example. There we go. So this is sample problem 8.2 on page 330. Arrange magnesium oxide, calcium oxide, and strontium oxide in order of increasing lattice energy. Increasing lattice energy. Pen out here. We'll do green. Sure. I lost one of my clippy things. Thought that looks familiar. So be very careful with wording of questions when they ask for increasing versus decreasing, because I see a lot on tests when people get the order right but completely reversed, and I don't know if it's because they reversed the concept or because they were thinking decreasing but the question was asking increasing. I don't know. So be very careful. When I say words like this, increasing, I'm going to go ahead and write down, that means I go from what to what? Smallest to greatest. So I'm actually going to write down, this is my smallest, comes first, and this is my biggest, comes last, and that helps keep me on track. So magnesium oxide, calcium oxide, strontium oxide. Am I comparing charges or the distances here? Distances. All of these have the same charges. Magnesium, calcium, and strontium all have a charge of what? 2 plus. Good. And then they're all bonded to oxygen, which is 2 minus. So now we're looking at distances, which we're going to go back to that last example and compare the ionic radii. So in the last example, rather than referring to the table, we said, well, if I look at the table of ionic radii, I can look at the periodic table and tell which one would be the biggest. So I'm comparing magnesium, calcium, and strontium. Looking at the periodic table, which one of those has the biggest radius? Why? Biggest radius, not biggest lattice energy. Yeah, you jumped ahead. Strontium has the biggest radius because it is the good, it has the most shells. So magnesium has the smallest radius. And then calcium is right in the middle. So off of that, which one would have the smallest lattice energy? Strontium. Good. Strontium oxide has the smallest lattice energy, Le, because it has the biggest radius, so the distance between them is the greatest. Which one has the biggest lattice energy? Magnesium oxide, and then who's in the middle? Calcium oxide. So again, that's all I'll ask you about lattice energies. Put it in order of increasing or decreasing, or tell me which one's greater and why. Sound good? Ready to move on? All right, let's move on. Sure, keep them. So we're moving on to section 3, which starts on page 334, and we're talking about now covalent bonding. So if you've ever been around any science class that even touched on chemistry, you've probably heard about the big difference between ionic and covalent bonding. What is the big difference about how they handle their electrons? Sharing. I thought I heard that word. There's the key word. Which one shares, covalent or ionic? Covalent. Sharing is caring, right? Covalent bonds share electrons, while the ionic bonds do what with their electrons? Transfer. They steal them. The anion is going to steal them away from the cation. So covalent bonding is the first idea of we're going to, instead of transferring those electrons, we're going to share them. So This is the start of Lewis theory of bonding, and so we're going to use our Lewis dot structures to show this. So let's start with the smallest, simplest covalent bond we have, and that is the one we would have between two hydrogen atoms. All right, so here's two hydrogen atoms facing each other. Let's see what happens between them. If I have one electron on a hydrogen atom, is that hydrogen atom happy? No. Why is hydrogen not happy sitting there with one electron? How many electrons does hydrogen want? 2. Why does he want 2? Full shell, because he's in the first row of the periodic table, so the only thing in his valence shell is the S, and S can hold 2. The other thing we say is that everybody wants to be like which group? The noble gases, the cool kids. Everybody wants to be like the cool kids. So what noble gas does helium, or I gave you the answer, what noble gas does hydrogen really want to be? Helium. So he wants 2 electrons. So this hydrogen's sitting here thinking, I really want another electron. And he sees that other electron over there, and he's going to say, oh, I'm going to grab that electron and pull it towards me. But what's happening at the same time over there? What's this hydrogen thinking? Wants the same thing. So he's going to reach over and he's going to grab that one and start pulling on it. And as they pull and pull and pull, what happens to the distance between them? They get closer and closer to the point where we end up with something that looks like this. Now, both of these hydrogens are close enough to those electrons that they both think they have 2 electrons, and they're both happy, but the truth is they're sharing those electrons. So a covalent bond is a shared pair of electrons. Shared pair of electrons. Shared pair of electrons. We usually write it with a line, so we would write it like this, hydrogen dash hydrogen. So this line right here represents that shared pair of electrons. There are 2 electrons inside of that line. In the Lewis theory of bonding, I like to call this connect the dot bonding. You can connect any dots that are single to another dot that is single. If there are already 2 electrons on that side, then it's already happy. It's already got a full orbital, because remember, the sides of the atom are representing the orbitals, and we have 4 orbitals in our valence shell. So for example, if I had fluorine, how many electron dots would I have around a fluorine in the Lewis dot model? 7. So I'm going to do 1 per side, 1, 2, 3, 4, 5, 6, 7. That's a little wonky, but that's okay. So looking at this, how many spaces does fluorine have available for bonding? Just 1. Just this dot right here is available for bonding. The others are already filled. If we were considering this as the number, as the orbitals, the 4 orbitals, these other 3 sides already have 2 electrons. They're already paired. There's no spaces available. So we're going to come along here with a hydrogen that has 1 dot. Now, hydrogen really wants 2 electrons because he wants to look like helium. How many electrons, how many valence electrons, we'll just say that valence electrons does fluorine want? Wants 8 because it wants to be a noble gas. With the exception of helium, all the noble gases have 8. So what are they going to do here? They're going to try, hydrogen's going to try and pull on that valence electron of fluorine, and then fluorine's going to do the same thing with the hydrogen, and we're going to connect the dots. So watch very carefully. This is connect the dots. From one dot to the other dot, I have made a bond. That is Lewis theory of bonding. Connect the dots. You connect from a single dot to a single dot. Let's look at something that has a few more atoms. Let's look at an oxygen atom. So oxygen has 6 dots. 1, 2, 3, 4, 5, 6. 2, a hydrogen, and a hydrogen. So on the oxygen, just looking at the Lewis dot structure of oxygen, how many bonds can oxygen make? 2. It can make 2 because it has 2 electrons that are sitting there by themselves. So we would say that oxygen can make 2 electrons. Hydrogen can make Oxygen can make 2 bonds. Hydrogen can make how many? 1. So when I connect the dots from hydrogen to oxygen, I would make a bond right there, and the same thing on the other side. And what molecule have I just made? H2O, water. Just move it over here. Just go over here so I have more room. All right. Let's look at carbon. How many dots are around carbon? 4. 1, 2, 3, 4. So how many bonds does carbon want? 4. In the basic Lewis theory, the maximum number of bonds you can have around any atom is 4. We're going to talk in chapter 9 or in a little bit about how you can actually expand that, but for now we're just going to say 4. So that's why carbon is such an important element, because it can make 4 bonds. Why is carbon an important element again? Because what? Well, why is it more important for us? It makes us, right? We are what-based life forms? Carbon-based life forms, because our organic chemistry, the chemistry of the molecules that make us, is based on what element? Carbon. Carbon, most abundant element in the earth, right, is carbon. So in this ability to make 4 bonds is why it is such a versatile element that is so useful in building our molecules. So if it can make 4 bonds, let's come along with something that can only make 2 bonds. Let's say oxygen. So on the general idea of Lewis theory, I'm going to put these off to the side just because it's going to make it easier on us in a second. Oxygen can make 2 bonds, and if I put another oxygen over here, let's say it is also going to make 2 bonds here. Am I going to have 1 line between these guys or 2? 2. So let's do connect the dots again. So I'm going to connect these dots. Those look familiar. But I can also connect from this single carbon dot to that oxygen single dot, from this one to this one. That kind of looks weird. Let's make it a little bit neater, redraw it. So I'm going to draw the carbon, 2 lines out to 1 oxygen. That oxygen has 2 electron pairs by itself. Make that dot, lost my dot. So I'm going to put 2 electron pairs over here. On the other side, and what molecule did I just make? Perfect, carbon dioxide. So that would be the Lewis dot structure for carbon dioxide. Let's go back and double check some of these things. Does this oxygen right here think it has 8 electrons? Does it feel like a noble gas in this configuration? It's got 2, 4 electrons all to itself, and then how many electrons is it sharing? 4. Each of these lines is 2, so that's 4 more. So does that oxygen feel like it has 8? Yes. And then the one on the other side that's the mirror image, same thing. Does the carbon in the middle feel like he has 8? Yeah, that's not what I was hitting. Yes, he has these 4 and those 4. He feels like he has 8. A good Lewis dot structure, everybody will feel like they have the electron configuration of a noble gas, which means that each hydrogen is going to feel like it has 2. Everything on the second row and below is going to feel like it has 8. Left off the ion dioxide. Told you I was not an English teacher, sorry. Bad speller. So how do we feel about the connect the dots method of bonding? Do that? Pretty good? You can also have a triple bond. For example, let's just do one quick example of something that would form a triple bond. Nitrogen. Nitrogen. How many dots would be on my Lewis dot structure for nitrogen? 5. Good. 1, 2, 3, 4, 5. So it can make how many bonds? 3. So if I came up against it with 3 hydrogens, I could make 1, 2, 3 bonds. What molecule did I just make? Ammonia, right? Ammonia, NH3. Boom. It looks like this. I have a nitrogen, single bonds to 3 hydrogens, and then the nitrogen also has a little lone pair. So the nitrogen feels like it has 2, 4, 6, 8 electrons. Or I could take this nitrogen and I could face it up against another nitrogen. If I count my dots correctly, that would help. Let's do this. 1, 2, 3, 4, and then 5. Okay. So when these two nitrogens see each other, nitrogen is very unstable as a monatomic atom. That's why back in chapter 2, I said if I just say nitrogen gas, I really mean N what? 2, because a nitrogen atom by itself is very unstable because it's not happy because it has 5 electrons, and that is an unhappy atom that has 5 valence electrons. It wants 8. So if it sees another unhappy nitrogen atom, it's going to bond with it to make them both happy. How many bonds will it make to this nitrogen? 3. Let's connect the dots. 1, 2, 3. So again, we're connecting all the single dots. So we end up with, if we make this a little bit prettier, a what kind of bond would this be? Triple bond. Good. So we have single bonds, double bonds, and triple bonds. Any questions about that? If you go on to the next page, page 336, it talks about in general, some general physical properties of covalent compounds versus ionic, things like their melting point and such. But you can read on that table on your own. What I did want to point out, though, was the bond lengths here. So let's go to the bond length table. So this bond length table is on page 336. This is just a comparison of covalent bond lengths. Now, because covalent bonds are sharing electrons, we don't just add the atomic radius of each of the atoms like we did with ionic. Because they're sharing, their electron clouds will overlap, and you'll actually end up with a smaller bond length. Now, the more they share, so if I'm comparing, say, single, double, and triple bond, let's just make this bigger for a second. Let's compare these. Actually, single, double versus triple. Let's look at that for carbon. So this bond length, which is in picometers, 10 to the negative 12 meters. What happens as these carbons form more bonds with each other and share more electrons? What happens to their length between them? It gets smaller because the more you share, the what you become together. Further or closer? Closer together. Sharing is caring, right? The more you share, the closer you become together. I keep on trying to convince my kids of that, and they're like, but I don't want to be close to my brother. He's gross. So the more you share, the more your electron clouds will overlap, the closer you'll become together, and the shorter your bond length. So I'm not going to ask you specific numbers, but I do need you to know that concept. For the same two elements, a single bond is always going to be the longest bond. A double bond will be shorter, and the triple bond will be the shortest bond. So the more sharing, the more overlap, the shorter the bond length. So just be able to know that concept. Page 336.